Thursday. This Thursday is the 2nd. So a week from Thursday, the last class is on December 9th. We have today.
And then the finals after that.
And our final is the following week. Again, I'm not sure exactly which day it is. I'm waiting for the schedule from the registrar. But it is the week, the following week is our final. And again, your final is going to be just like the midterm. It's going to be on Blackboard. You are going to be given 2 hours. It's going to be a multiple choice test. It's going to consist of 30 questions, not the preview test for the final. That has 40 questions, but the actual final will be 30 multiple choice questions, and you'll be given 2 hours to complete it. Any other questions?
No, that's all.
Okay, great. So let's look at this first question. This is a review of the last of our trigonometry, just as a reminder of the trigonometry. We're told that the tangent of A is 7/11, and we want to find what the cosine of A is in simplest form. And I didn't give you a triangle, but we can draw a triangle. We know that the tangent, remember, our SOHCAHTOA reminds us that the sine is the opposite over a hypotenuse. The cosine is adjacent over the hypotenuse, and the tangent is opposite over adjacent. So when I tell you the tangent of A is 7/11, it means that we have a right triangle. There is a right triangle, and we can call this angle A, in which the opposite side is going to be 7, because it's up, and the adjacent side is going to be 11. So I'm going to draw a triangle. It's not the only triangle that I could draw, but this one is a very easy triangle to draw that will have that. I'll put, this is my, remember, opposite is a cross, so this is where my 7 is going to be. This is my hypotenuse, which we don't know because they didn't tell us anything. They told us only about tangent. And this is my adjacent, and I was told it's the adjacent should be 11. So we can draw a right triangle. Remember, this is my right angle, with the opposite side being 7 and the adjacent side being 11, and therefore the tangent is 7/11. We can then use this triangle to figure out what the cosine is. Now the cosine is the adjacent over the hypotenuse. So in order to do this, what we have to figure out is what is the hypotenuse. We know the adjacent is 11. What is the hypotenuse? But we know every time we have a right triangle, if we have two sides, we can use our Pythagorean theorem, a squared plus b squared equaling c squared, to figure out the third side of that right triangle. So here's I'm going to do 7 squared plus 11 squared equals c squared. The c is always the hypotenuse. And working this out over here, I'm going to go this over here. So now I have 7 squared, which is 49, plus 11 squared, which is 121, equals c squared. And when I add these up, I get 170 equals c squared. And therefore, c would be the square root of 170. Now, I usually look to see if I can simplify this radical. Notice it said in simplest form. It didn't say in decimal form. It didn't say the nearest tenth or nearest hundredth. It said simplest form, which means they want us to leave the radical in it. But they want us to simplify the radical. But the only thing I can break 17 up in 170 up into is 17 and 10. Neither of those are a perfect square. So I can't simplify this. So I'm just going to leave it the square root of 170. So therefore, my cosine of A is going to be the adjacent, which he said is 11, because it's right over here, over the square root of 170. Now, this is a perfectly good answer, except when we say simplest form, we don't want to leave a radical in the denominator. So what I do is I multiply the top and the bottom by the square root of 170 so I can rationalize the denominator, make the denominator into a number without any radical. So this will become 11 times the square root of 170. And of course, when we multiply radical 170 by radical 170, it just gives us the 170. Remember, we spent time doing radicals. So my answer for this question would be 11 radical 170 over 170. Again, I was not asked to do this in decimal form. So therefore, just in simplest form, this is what we would have given as the answer. Okay, let's now look at this next question. Should not have. We have an example where we're told, and this was going into our last chapter, our chapter on exponential functions and logarithmic functions. And we said we could recognize something being an exponential function where if we have a variable, the variable is in the exponent. We're going to know what the base is. In this case, the base we're using is 2. But our unknown, our variable is going to be in the exponent. And the question here being asked is, if f of x is 2 to the 3 to the x power, what is find f of -1? Which means, of course, replace the x by -1. So I have 2 to the 3rd to the -1 exponent. Let's remember that when you have something that has 2 exponents on it, it's a number with an exponent and then it's raised to a second exponent. What we can do to those 2 exponents is multiply them. So when I multiply the 3 times the -1, this is equivalent to saying this is 2 to the -3. And now we have to figure out what 2 to the -3 is. We could, of course, take out a calculator, but if we don't want to do it with a calculator, if we want to do it with our just figuring it out, we know that when we have a negative exponent, it takes the reciprocal. This is really like 2 to the -3 over 1. To change this negative exponent, we're going to move it from the numerator into the denominator. This will become 2 to the 3 in the denominator. Of course, it's not like nothing is left on top. Whatever is gone, what we're left with is just a 1. So this is equivalent to saying 1 over 2 to the 3rd. Again, don't forget, a negative exponent takes a reciprocal. And the 2 to the 3rd we can figure out is 2 times 2 times 2, which is 8. So this answer is 1 over 8. We talked about positive exponents, negative exponents, fractional exponents. Let's just review that when we said when we have a fractional exponent, for example, if I give you 64 to the 1/3 power, that, remember, a fractional exponent means it really is a radical. This really means radical 64, where the index is the denominator here. In other words, the index here would be 3. This means the cube root of 64. Again, you could do this on your calculator. If you're doing it on your calculator here, you could put in the 64, press your exponent button, and then do parentheses 1 divided by 3 to indicate to the calculator that you want to do the exponent being the whole 1/3. You don't put in that parentheses, it'll think just the first number is going to be the exponent. Or you could work it out this way, and either way, the cube root of 64 turns out to be 4. So your answer in this case would be 4. So a fractional exponent indicates a radical. The simplest fractional exponent is 1/2. If I give you 25 to the 1/2 power, that's the same thing as saying the square root of 25. The index here is 2. When we have an index of 2, we don't put the 2 in there. Any other radical, we put in a number over here. If we don't put in a number over here, it's understood that the index is 2. And the square root of 25, of course, would be 5. Again, you could stick this into your calculator, or you could just figure it out on your own. That pretty much takes us to where we were last Tuesday. I think we mentioned solving equations that are what we call exponential equations. So let's just do one like that. And then we're going to talk about this new topic called logarithms. So suppose I gave you an equation that looks like this. I'm actually looking at the sheet that I'll post it later. Suppose I give you 5 to the 10 minus 2x equals 125. Again, this is called an exponential equation because our variable is in the exponent. And what we would like to do is try and get both sides of the equation expressed in terms of the same base. The base being used on this side is 5. This is 5 to the 10 minus 2x. We're going to try and get this side expressed in terms of base 5 as well. So how do I do that? Well, I just start multiplying by 5s. 5 times 5 is 25. 25 times 5 is 125. I get to 125 by doing 5 multiplied 3 times. In other words, this is equivalent to saying 5 to the 3rd power. Now, it's not always going to be possible to get both sides being written in terms of the same base. But if we can, then that's what we're going to do. Now, in this case, we have we've simplified this to 5 to the 10 minus 2x equals 5 to the third power. Rewriting 125 is 5 to the third. Now, since they both have the same base, their exponents must be equal as well, which means that the 10 minus 2x, the exponent on this 5, has to equal the 3, the exponent on this 5. In other words, I can just ignore the 5s now and just look at the exponents. And this gives me a relatively easy exponent equation to solve. I'll just bring this 10 to the other side. So that'll give me negative 2x equals 7 minus 10, which is negative 7. 3 minus negative 10 is 3 minus 10 is negative 7. And then I divide both sides by negative 2. And of course, a negative and a negative gives me a positive, so my answer becomes 7 over 2. So that's how we solve a exponential equation. Now I'm going to give you one to try while I take attendance. Okay, suppose I give you this equation. Two to the 3x minus 1 equals 32. See if you could figure out what x is equal to. Anytime I am taking attendance. Jesus Antonio. Jackson Avila. Hi, Jackson. Tiffany. Kayla. Tishana. Hi, how are you? Dion.
Good morning, Professor. I'm here.
Hi,
How are you?
how are you?
Fine, thank you.
What? Wensley? Tatiana? Tatiana here? Awa? Hi, how are you? Ashay? Hi. Eliana? Emily? Anastasia? Zenabu? Ismail?
Good morning.
Hi, good morning. Jaden? Ashiana. Hi, good morning. Anijah. Thomas.
Yeah,
Hi, good morning.
good morning.
Paul.
Here.
Hi. Ashley. Angelica.
Here.
Hi, how are you? Tayon. Hi, good morning. Akim. Craig. Giovanni. Devonly. Najay. Okay. Okay, see, we already have an answer to our question. Tashana, Awa, great. It looks like you got the same answer. Let's see if we all get the same answer to it. Okay. So what we have to remember, well, this side is written in terms of 2. It's in what I call base 2. So I'm going to have to try and get 32 written in terms of base 2, which means I want to write 32 as 2 to some exponent. So again, I go through my numbers. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. 16 times 2 is 32. In other words, if I multiply 2 5 times, I will get to 32. So I can rewrite the 32 as 2 to the 5th power. So we have now 2 to the 3x minus 1 equaling 2 to the 5th, which means now, since they're both in base 2, I can just set the exponents equal. 3x minus 1 has to equal the 5. I'll bring this 1 over to the other side because now I just have to solve this equation. I get to 3x equals 6. And dividing by 3, it gives me x equals 2, which is, I see a bunch of people got that answer. Excellent. Okay, good, excellent. So I want to now introduce something, a new topic, which really you'll see how it ties in with what we were talking about here, these exponential equations. Again, let me just mention, if this number wouldn't have been 32, let's say this number would have been 30, I would never have been able to put it as 2 to some exponent. It's not always possible to solve these exponential equations this way. We're going to learn, after we do this next topic, we're going to learn how to deal with these kind of examples if we can't get both sides to be in terms of the same base. Okay, so what I want to do is talk about something called logarithms. Something called a logarithm. It's a strange word. You may, if you've looked at your calculator, see something that looks like this on one of the buttons of your calculator. The abbreviation for the word logarithm is log. And you're going to see something that looks like this, for example. Log with a subscript, the number next to it, equaling another number. There are going to be three numbers involved in this logarithmic statement. There's going to be this number that's what we call a subscript, which is we're going to call it the base. This is the number, and the number on the other side is actually the logarithm. And this is how it's read. The log base 5 of 25 equals 2. Let me read it again. The log base 5 of 25 equals 2. And what does that mean? If instead of the word log, you read the word exponent, because that's what a logarithm is. It's actually an exponent. Let's use the word exponent. The exponent of base 5 that gives us 25 equals 2. The exponent that you should put on the base 5 to get to 25 is 2. In other words, the log is simply an exponent. And all the things that we learned about exponents are going to apply to this new thing called a logarithm. It's an exponential expression written in a different way. It's just a different setup. I'm going to change this from the logarithmic setup to what's called the exponential setup. How do we do that? Well, the subscript is the number that's going to be the base. The number on the other side of the word log, what the log is equal to. Remember, log means exponent. The exponent is equal to, so the number on the other side is the exponent. So I'm going to do 5 to the exponent 2 is going to give me this number. What's the difference between logs and exponents? Well, the difference is the focus. If I write something like 5 to the 2, I'm giving the base, I'm giving you the exponent, I'm asking you, what are you getting as the final answer? Whereas if I'm using a log, I'm still giving you the base, but what I'm giving you is the final answer and trying to figure out what the exponent is. It's just as if I'm giving you the answer and asking you what's the question, sort of like Jeopardy. Now, you have to be very careful. This subscript here, this 5, that always has to be a positive number. We can't use a base that's negative. And on top of it, the number that you're taking the log of, this number over here, that also has to be positive, because that's a number you get. Put 5 to any exponent, you're not ever going to get a negative number. So you can never take the log of a negative number. You can never take the log of 0. The number that's next to the word log always has to be a positive number. It can be a fraction, it can be a decimal, it can be a whole number, but it must be positive. Let's just write down the rule for switching from what we call logarithmic form to exponential form. I'm going to write it as a ABC type of thing. If I write the log, and I'm writing a little small b for base of A is going to equal C, that means that the base, the B, to the exponent, which is the C, will equal A. These two things mean exactly the same thing. They're just two different expressions of the same idea. One where we focus on the base and the exponent to get the answer. One where we have the base and the called the answer, and we try to figure out the exponent. In other words, I could give you a question that looks like this. Find log base 2 of 32. What am I asking you? Well, let's call this x, because I don't know what it is. And it's much easier, because we're so much more familiar with exponents than we are with log, to rewrite our question in exponential form. Sometimes just changing the question from the log format to the exponential format will enable you to answer the question. So let's put this in exponential form. Remember, my base is always a subscript, which in this case is 2. My exponent is always the number that the log is equal to. Log means exponent, so the exponent is equal to, in this case, x. So this is saying 2 to the x is equal to this number over here, the 32. Remember, there are always going to be these 3 numbers, the base, the number, and on the other side, the number that's equal to the log or exponent. Now I look at this, I have an exponential equation. I want to know 2 to what exponent will give me 32. Well, we just did that type of question. 2 to the 32, 2, 4, 8, 16, 32 was 2 to the 5th. It was the same exact numbers. So that must mean that my x is equal to 5. So basically, finding a log is equivalent to solving an exponential equation. Okay, I'm going to put a couple of questions on the board. I want you to change them from the log format to the exponential format. And if there's an x in it, figure out what the x is. I'm going to put on a couple of problems. Okay. I'll leave that on the board as a hint. Okay, number 1. See if you could do this one. First of all, convert or change to exponential form. Okay, so this is, I'm giving you all 3 numbers, but it's written in log form. I want you to write in exponential form. And number 2, see if you can solve this. Gonna give you a couple of minutes to try that. Anybody want to try rewriting this? Anybody want to tell me what to do? I know it's a little bit hard to write this on the chat.
Professor, can I give it a shot? I don't know if I got it right. I'm just gonna give it a shot.
Okay, we'll let you know. Okay,
Okay. So what I wrote was 7 negative 2, exponent 7 exponent negative 2 equals to 1 over
Is
49.
7 an exponent or not?
No, it's not. 7 is not the exponent.
7
It's
is a
negative
base.
2.
Negative 2 is the exponent.
Yes, equals to 49 or 1 over 49.
Perfect.
That's what I wrote.
Absolutely perfect. Changing that, I wrote it a little bit differently. Usually I put the word log first and the number next, but this is absolutely perfect. The base is 7. The number on the other side of the word log, what the log is equal to is the exponent. So negative 2 is the exponent, and that equals to the number that's next to the word log, which is 1 over 49. And if you look at this expression, it didn't look so clear when you wrote it in log form. I mean, to me it does, because I'm sort of used to doing logs a lot of times. But if you're just starting with logs, it's a little bit harder to do, to think that way. But look at it. What does 7 to the negative 2 mean? It means, the negative means to put 1 over it, and the 2 means 7 squared, which is 49. So that really makes sense that 7 to the negative 2 is 1 over 49. So it's saying this exact same expression. This is the log format. This is the exponential form. Okay, did anybody come up with an answer for number 2?
Is it x equal 81? So it's 3.
Well,
Square root 4.
how about first putting it in exponential form?
So what I wrote was 3 square root 4 equals x.
Square root of 4?
Yes, that's how I wrote it. I'm not sure.
Okay, obviously 3 is the base. What is the exponent going to be?
So now I'm thinking about it. Is it going to be 4. No.
Absolutely. Remember, the log, the number on the other side of the word log, of the other side of the equal sign, that number is the exponent. The exponent is going to be
4.
4. And that's going to be equal to our
X.
x. Okay, I just
So do we find
rewrote,
the X?
and we want to find the x. Can you figure out what x is now?
It's 81.
It's
isn't it
81, absolutely. Did you say 81 is the answer? It was just I think you were the thing that you were saying, that the square root. You didn't mean the square root. You mean the x. You meant the exponent. I think it was just the way
I
you said
did.
it.
Yes, yes.
Okay, so notice it looked very hard. What does log base 3 of x equals 4 mean? But once you change it from its log format to the exponential format, again, the subscript is the number that is the base, the number that's going to get the exponent. The number on the other side is the exponent. That equals what's next to the word log. So 3 to the 4 equals x, and of course 3 to the 4th is 81. And the answer to here, and we did get some answers on the chat as well. 81. Excellent, Ella. Okay, so now that we see that logarithms are really not anything so new, it's just another way of saying something that we've already dealt with. Let's talk about some of the other things that come together with logs. First of all, we're going to talk about what I call the rules of log arithmetic, or they generally call it the properties of logs. The properties of logarithms. Now remember, when I'm talking about the properties of logarithms, I'm really talking about the properties of exponents. So there are basically 4 rules that are going to apply to logarithms. Rule number 1, or property number 1. If I have the log base b of 2 numbers, let's say the numbers are x and y, okay? I'm multiplying 2 numbers together, x times y. What do you think we should do to their logs? Remember, the logs are exponents. In order to figure this out, I'm going to give you some examples. And I think if we look at the examples, we'll be able to figure out what the rule should be. Now, I'm just going to mention, on your calculator, if you have a scientific calculator, there are actually 2 buttons that have to do with logs. One button says LOG, and the button probably right next to it or or under it says LN. Now, it doesn't say IN. Sometimes it looks like, they use the lowercase, so the L looks like just a straight line. You think it's an I. It's not, it's LN. These 2 buttons are what we call log buttons. I'm not going to talk about what they are right now. I'm probably going to get to that next time. But I am going to mention just the plain log button. The log button, when you look at it, looks a little strange, because whenever we write the word log, we always write a subscript with it. And I don't see any subscript written with it. And that's not like a mistake. it happens to be understood that if the word log is written and there's no base written next to it, the base is understood to be the number 10. Our whole number system is based on the tens. So it seems that if we're going to pick any number that would be the easiest to deal with in terms of exponents, probably 10 is the easiest. Let's face it. If I do 10 squared, I get 100. If I do 10 to the third, I get 1,000. In other words, the exponent of the 10 tells you how many zeros there are. It's really an easy number to multiply by. So on our calculator, if we're going to pick any number to use as a base, since our whole number system is based on tens, very often that's what we do. We pick, and that's exactly what the calculators do. Not only that, since this is probably the most common number used as a base is 10, we call logarithms whose base is 10 are called common logarithms. If I ever say I'm talking about the common log, I mean I'm talking about a log and the base of that log is 10. And not only that, if I just write the word log and I don't put in any number as a base, it's not that I forgot the base. It means the base that's being used is 10. So I could ask you a question like this. Find log 1,000. And it wouldn't be that I'm making a mistake. I didn't leave out the base. When the base is not written in, it's understood that the base really is 10. There's an invisible 10 written next to the word log. Anytime the word log is written and there's no subscript, the base is understood to be 10. Let's see if we could find this log. Well, let's call it X because I don't know what it is. And let's change it to, from the log format, this is what we're doing a lot of, from the log format, let's write it as in exponential form. So in exponential form, my base would be 10, my exponent would be X, and 10 to the X equals 1,000, tells me that the X is 3. And that's the beauty of using tens, because the exponent is equal to how many zeros there are. 10 squared is 10 to the 2, is 100, 2 zeros, 10 to the third is 1,000, 3 zeros, 10 to the sixth is 1,000,000, which is 6 zeros. So the number of zeros in the number is equal to the exponent. Okay. So I'm going to do demonstrations using log base 10 because it's so easy to work with. Okay. So here's what we're going to do. Suppose I have my number X, let's call number X 100, and let's call number Y 1,000. What is the log of X? Remember, I didn't put any base in here, it's understood to be 10. 10 to what exponent will give me 100? Remember, all you have to do is count the zeros. It's 2. What is the log of Y? 10 to what exponent will give us 1,000? Remember, the log is the exponent, no base is written here, so it's 10. what exponent will I put to 10 to get 1,000? And I think we'll all agree that it has to be 3. Okay, let's now figure out what xy is equal to. If I multiply the x times the y, I'm multiplying 100 times 1,000, I'm getting 100,000. So what then is the log of xy? Well, 10 to what exponent? Log is what 10 to what exponent will give me 100,000. Again, all I do is count the zeros. 1, 2, 3, 4, 5. The log of xy is 5. And look what happened. When I multiply the numbers x times y, what am I doing to their logs? I'm not multiplying them. I'm not doing 2 times 3. I'm doing 2 plus 3 to get the 5. In other words, when I'm multiplying two numbers, what I'm doing to their logs is adding them. And that makes perfect sense if you think about it, because when you're multiplying numbers, what you do to the exponents is you add them. Remember, the logs are exponents. So my first rule in log, my first property of log, my first rule in logarithmetic is that if I have two numbers being multiplied, then what I do to their logs is I add them. In other words, the log of x, log base b of xy is the log base b of x plus the log base b of y. Similarly, let's say, let's take a different x and a different y. Suppose I take my x to be 100,000. And suppose we take my y to be 100. Now, it's very easy to figure out in base 10, the log of x. Remember, we just had to count the zeros. 1, 2, 3, 4, 5. This is the same as 10 to the 5th. So my log is the 5. Remember, the log is the exponent. What is the log of y? Well, 10 to what exponent will give me 100? Obviously 10 to the 2. The log of y is 2. Again, all I have to do is count the zeros. Now, what if I do x divided by y? What is 100,000 divided by 100 equal to? Well, that's easy. 100,000 divided by 100 is 1,000. So the log of x divided by y is what? Well, how many zeros do we have? 3. And if you look at it, the log of x divided by y is not the 5 divided by 2, it's the 5 minus the 2. And that makes sense also because when we're dividing numbers, what do we do to the exponents? We subtract the exponents. The logs are exponents. So therefore, my second rule, my second property of logs is that the log base b of x divided by y So the second rule is if we're dividing two numbers, then what we do to their logs is we subtract. So this is log base b of x minus the log base b of y. Okay. The third rule. Third rule is going to have to do with when you have exponents on your logs. So let's say we take x to be 100. And again, we know that the log of x then is equal to 2 because there are two zeros. Remember, I'm using log base 10 as a demonstration because it's easy to work with. Plain log means log base 10. Okay, now let's do x cubed, which means I'm doing 100 cubed. I'm doing 100 to the third power. Now, the easy way to do this is to change the 100 to 10 squared. This is the same as saying 10 squared to the third power. And we know when we have two exponents on a number, what we do to the exponents is that we multiply them. This becomes 2 times 3, so it becomes 10 to the 6. So let's see how this works out in terms of the logs. We now want to do the log of x to the third. And I know my answer, x to the third, is 10 to the 6th. The log of 10 of x to the third is going to be 6, because what I've really done is multiply these two exponents together. The original 2, which is the log of x, is being multiplied by this new exponent 3. We're taking this 3 and multiplying it by the 2. In other words, what we did is we took the 3 and multiplied it by the log of x. That's how I got my 6. So my new rule that has to do with exponents looks like this. If I have the log base b of x to some exponent, all I have to do is take that exponent, like this 3, that in this case n, and multiply it by, just like, I don't even have to write the multiplication, I can just write multiplied by the log of x. In other words, the exponent becomes the coefficient. Why? Because this log of x is an exponent. And if you have something with an exponent raised to a second exponent, you multiply those two exponents together. You take the log of x and multiply by 3 to get the 6. So the easiest way to say this final rule is to say the log base b of x to the nth power, take that exponent and put it in front, make it a coefficient, multiply by that exponent. Actually, this even works for radicals. Because let's say I have the fourth root of x. I have a radical, the index is 4. Remember, when we started this chapter, we started talking and we said, we're not going to use radicals in this chapter. we're only going to express our radicals as fractional exponents. The fourth root of x is the same as x to the 1/4. The square root of x, most important one, is x to the 1/2. The cube root of x, if your index is 3, it means x to the 1/3. So therefore, if I have something, and this exponent, if I have a radical, I just change the radical to an exponent and use the exponent rule. So basically, these three rules take care of the properties of logs. Let's see how this can be used. Okay, I hope you have these written down because I have to well, let me just, just stick below it, try to stick as low as possible here. Suppose I gave you an expression that looks like this. Log x squared y to the 4th. Now, first of all, if you notice, I didn't write any base. So you know that my base that I'm working with here is 10. This is a common log. But the question is, here's the wording of the question. Use the three properties of logarithms to expand each expression. They want these to be written in what we call expanded form. Sometimes it just says write in expanded form. Sometimes it just means expand. We want to write this expression in terms of individual logs. What's the log? And I'm going to do this in 2 steps. I'm going to use these 3 rules and I'm going to expand this. So the first thing I look for is anything that has to do with either multiplication or division. And in this case, we have 2 things being multiplied. We have the x squared being multiplied by the y/4. So I know from the rule that when I'm multiplying things, what I do to their logs is I add them. So I can expand this to log x squared plus log y/4. Notice I have to put the word log in front of them because I'm telling you what to do, not to the numbers, but to the logs of the numbers, to the exponents of the numbers. So that's step number 1. But I can go even further because I know every time I have an exponent can be put as a coefficient, just like over here. This exponent comes out in front because you want to multiply the log of x is itself an exponent. So I'm multiplying an exponent by an exponent. So therefore, I'm going to bring this 2 in front. So this is going to be 2 log x. And this 4, this is also an exponent. So I'm going to put this as 4 log y. And this would be this expression expanded in terms of individual logs. Let's do another example, and then I'm going to give you one to try. And I'm going to erase this now because I just need the board. But we're going to remember you should have those rules written down. So let's say I have this example. I'll do a simple one and then I'll do one that's a little bit more complicated. Suppose I have log base 2 of the square root of x times y divided by z to the third power. Okay? How do I expand this expression? Well, first step first. This has nothing to do with logs, but I see a radical. Anytime I see a radical in this chapter, anything that has to do with logs or exponential functions, I want to rewrite that radical as an exponent, remembering that the square root of x is the same thing as x to the 1/2 power. Remember, every radical can be written as a fractional exponent. So this really is telling me that we're doing log base 2 of x to the 1/2 times y divided by z to the third power. Now this is, I can't leave out this 2 because now we're dealing with base 2. If we leave out the number 2, I just have to bring it around. I just have to write it, because if I bring it out, it'll look like I'm dealing with log base 10, and I'm not. My base I'm using in this case is 2, but I'm concentrating on expanding. I just want to first look at where I have to multiply or divide. So here I'm multiplying the x to the 1/2 times the y, and I'm dividing it by the z to the third. And I know when I'm dealing with logs, where I multiply, I add logs. Where I divide, I subtract logs. So I could write this as log base 2 of x to the 1/2 plus, I'm multiplying things, so it has to be plus log base 2 of y minus, because I'm dividing, and when I divide, I subtract, and whatever is in the denominator has to be subtracted because everything in the denominator is being divided. So I'm subtracting the log base 2 of z to the third. So I first take care of where I have multiplications, I add, where I have divisions, I subtract. Then I go back. At any place I see an exponent, I put the exponent in front as a coefficient. So this will become 1/2 log base 2 of x plus log base 2 of y minus 3, here's an exponent, so that has to go in front, log base 2 of z. All I'm doing is making use of those 3 rules of log arithmetic, or the properties of the logs. Okay. Let's do, let me give you one to try. Okay, here's another example. I'm gonna let you try this one. We have log base 7 of the cube root of x divided by z squared y. Okay, I'm going to give you a couple minutes to try that. Okay, let's work on this together. Again, whenever I see log and I see a radical, I want to change that radical from radical form, from a square root form to an exponent. And I know that the cube root of x is the same as x to the 1/3. So this really means do the log base 7 of x to the 1/3 divided by z squared times y. And now we're going to use those three property rules. First, we're going to work about the multiplication and division, and then we're going to work on the exponents. So I see that first of all, I have this x to the 1/3 being divided by z squared y. So when it comes to logs, I'm going to do the log base 7 of x to the 1/3 minus, and I'm going to have to subtract both of these because I'm dividing by both of these. They're both in the denominator, so they both don't do this plus this. Even though I'm multiplying these two together, what I'm actually doing is I'm dividing the whole expression by z squared. So it's minus log base 7 of z squared. And also minus log base 7 of y. I have to subtract this log of y as well because that y, it's in the denominator. Anything in the denominator is a divisor. It has to be subtracted. And now I go back and I put the exponents in front. So this will give me 1/3 log base 7 of x. Here's an exponent, so that 2 is going to come in front, minus 2 log base 7 of z. There's no exponent here, so I'll just write it minus log base 7 of y. And this is the most tricky thing here, is it looks like you're multiplying these two things together, but what you're looking at is what's it doing into the whole problem. And this y is just like the z squared is a divisor, so is the y, because anything in the denominator, anything underneath that fraction line is really being divided, used as a divisor, and therefore as a log has to be subtracted. I just want to do one more thing before I end the class. I'm going to, what if I gave you something like this? What if I gave you an expression in the expanded version and asked you to write it as a single log? In other words, suppose I gave you 2 log base 5 of x plus 1/3 log base 5 of y minus log base 5 of z. This thing has already been expanded. What if I want to go back to the original form, the single log? Okay, so again, I'm going to do it in 2 steps, but I'm going to do the steps backwards. Before, when I was expanding, I first did multiplication and division, and then I did exponents. So when I go backwards, I first look for the exponents and then the multiplication and division. Any number that's in front was originally an exponent. So this really is log base 5 of x squared, because this was a 2 in front, goes back to being the exponent 2. This becomes log base 5 of y to the 1/3 exponent. This 1/3 coefficient means it was originally an exponent. And this is minus log base 5 of z. Now, we're going to remember that, well, let's just first work it out and then I'll take care of the x. Now I look, any place that I see logs added, I know I'm going to be having to multiply the numbers. Any place I see a subtraction, I know that's going to have to be a division. So anything positive is going to go in the top of my fraction. Anything that has a negative sign in front of it is going to go into the denominator, because it's going to mean it's it's being divided by, and that means it goes in the denominator. So writing this as a single log, this will be log base 5. Okay, these two things are, now I just write the word log once. I'm going to do the x squared times the y 1/3. And this is minus, so that's going to go in the denominator, the z. The only thing is that it looks a little funny having an exponent of 1/3. Remember that the 1/3 exponent is the same as the cube root. So this can be written as log base 5 of x squared cube root of y divided by z. And this would be the example going backwards. This was the contracted version of this. They gave us the expanded version and wanted us to go back to the single log. Okay, this is where we're going to continue on Thursday. We're going to see how using these properties of logs can help us solve different types of equations. I am going to remind you that I'm not giving you any additional homework yet on Delta Math. There will be on Thursday, I will, but today I'm not. Once we finish talking about logs, I will give you an additional homework on Delta Math. But as of now, for Thursday, you have to finish up the test on Delta Math, test number 3 on Delta Math. Also, by this afternoon, there will be posted on Blackboard a pre-test for the final. That is a test for you to do. You're going to have 2 chances to do it. It has to be completed by December, I think the due date is December 13th. But it's not next week. It's 40 multiple choice questions. You're going to have 2 chances to do it. And I will pick as your mark the higher mark that you get when you have these 2 chances. You are given a 2-hour, you have to do it in a 2-hour sitting. It's 40 multiple choice questions. It's a prep for your final. Your final will be the week of the 13th. I don't know the exact time or date, but it'll be around in the week of the 13th. And you're going to be, your final will consist of 30 multiple choice questions on Blackboard, just similar to the way it was done for the midterm, similar to the way the test on Blackboard. So you have to, for Thursday, complete the test on Delta Math, and you have another almost 2 weeks to complete the test on CUNY Blackboard. Again, this is any work that it has to be completed, any tests that are missing, any homeworks that are missing have to be completed by the week of finals if you want to get credit for it. Any questions?
I have a math problem.
Okay.
So, like, let's say you have the value of CSC. How do you get the value of tan?
I'm sorry. Okay, let's. What do you have?
So it says CSCA
Okay, cosecant A
equals square root 29 over 5.
okay, and they want you to find tangent A?
Yeah,
Okay. So first of all, we have to remember what cosecant, this is, CSC means cosecant. The cosecant is the reciprocal of the sine. I will review these. I see I should have done this. I definitely will review this on Thursday about these reciprocal functions. There are the SOHCAHTOA is the sine, cosine, and tangent that you probably remember. The reciprocal ones, there are 3 other functions. One is the cosecant, is the reciprocal of the sine. The secant is the reciprocal of the cosine. And the cotangent, the COT, this is abbreviated CSC, cosecant. SEC, secant, is the reciprocal of cosine. Cotangent, COT, is the reciprocal of tangent. So if I tell you that the cosecant of A is the square root of 29 of 5, that's the same thing as saying that the sine of A, because the cosecant is the reciprocal of the sine, is 5 over radical 29. Now let's draw our triangle. Here's my A, B, C. Remember what the sine stands for. The sine is the opposite over the hypotenuse. So on my triangle, the opposite side, which is this one, I'm going to put as 5. And the square root of 29 is going to be the hypotenuse. So far, okay?
yeah.
Okay, but what did I want to find out? I wanted to find the tangent of A. And to find the tangent of A, tangent is TOA, is opposite over adjacent. So I know what the opposite side is, it's 5. That I know. But what I don't know is the adjacent side. So that I'm going to have to do using the Pythagorean theorem. I'm going to have to do 5 squared. Well, this I don't know. Let's call it B squared equals the square root of 29 squared. Right? A squared plus B squared equals C squared. So 5 squared is 25. B squared, we don't know. So we'll leave it B squared. The square root of 29 squared, well, the square root of 29 times the square root of 29 is just 29. So if I subtract 25 from both sides, I will get that B squared equals 4, which means the B has to equal 2. The third side of this triangle is 2. And now I can do the tangent is opposite 5 over adjacent 2. And my answer is 5 over 2. So what did you have to know? You have to know what the three trigonometric functions are: sine, cosine, tangent, cosecant, secant, and cotangent. And then you have to use the Pythagorean theorem. Okay, Demiolo, I don't know how to pronounce your name, but there is tutoring today, and he'll be able to do that type of thing from 12 to 2. And I sent you the link for our new SI. So if you have any other questions, again, if you have any questions, definitely go to tutoring, and we'll continue with this discussions. We'll do some more trigonometry, and we'll do some more logs on Thursday. Okay, have a good day, and I'll see you on Thursday.
Have a great day, Professor.
Bye-bye, you too.